Okay, we're gonna start for the very last presentation, something which was announced in many presentations this week. There is the evolution towards post-quantum, and it's important that we're ready for post-quantum, but actually the implementations of post-quantum we didn't cover yet. So that's gonna be Suparna explaining that to us. Okay, the floor is yours.
Yes. Thank you. Thank you for the introduction. Yes, as mentioned today, I'm going to covering some insights and challenges about post-quantum cryptography. And don't worry, I'll be staying in algorithmic domain so that most of us do understand almost everything. But if you do not, yeah, shout. Don't shout too much. Just ask question. Okay, I'll start with the background, very basic background about post-quantum cryptography. I'll be focusing on key encapsulation mechanism specifically, but the component I'll be talking about that covers, that is used in many different post-quantum schemes, including digital signatures, and also in FHE and in many places, actually. And after that component is polynomial multiplication, just a heads up. And apart from that, I'll be covering part of the thing that Benedict covered in the morning, side channel attacks, how it is exploited in post-quantum schemes, because it's an implementation. We are talking about implementation challenges, right? And then it's how we make sure it remains secure and some conclusions. So without further ado, I will start with the background that covers, as I mentioned, key encapsulation mechanism, public key and parameter choices. Now, this is the key encapsulation mechanism. This is key encapsulation mechanism that is used in the standard as well. You don't have to understand everything if you are not familiar with it. We do not need the whole algorithm, but it is an algorithm that is used by two parties, Alice and Bob. It was introduced by Frederick Volkerteren yesterday. And I'll not be covering the scheme, how it works and all, but I do need part of it. Here, if you see, this is a key encapsulation mechanism. There is two parties, Alice and Bob, and Alice does key generation, Bob used one of the keys, public keys, and do the encapsulation and then send back the ciphertext to Alice, and Alice does the decapsulation part. This is like two-party protocol, but it can be three parties and more. However, here, if you notice that we are using some sub-algorithms, like specifically PKE keygen or PKE encryption here, and here PK encryption and PK decryption. So we use multiple sub-algorithms inside it, and that looks like this, those algorithms. And if you notice, we also do not need the whole algorithm, so don't be frightened about that, like just seeing the length of the algorithm. So here I do need a part of this whole algorithm. Here, if you notice, in these algorithms, we have several polynomial multiplications. This, apart from the hash function that is used several times during key encapsulation and also here in PRF, apart from those, these polynomial multiplications are one of the most time-consuming and area-consuming operation that are used in post-quantum key encapsulation mechanism, most of the post-quantum key encapsulation mechanisms and digital signatures. So I will be covering mostly that multiplication techniques, how we actually implement them, what are the process, and how more specific instances which are used in several standards and many other candidate algorithms. So these are the parameters, some parameters which we need to understand polynomial multiplication, or at least understand how it would scale with complexity, because I'm gonna be staying in the algorithmic domain, talking about a little bit about complexity, but it scales with the cycles as well. Like it's very much corresponds to the cycles. So here, first of all, which is our NIST standard MLKM or Kyber. There, the parameter size is something like we have polynomials, 256 coefficient polynomials. We have a modulus, which is Z3329. And we do have a vector length. So here what we do multiple polynomial multiplication. It depends on vector, because we do vector multiplication. We have some matrix, and we do matrix vector multiplication. But the unit operation is polynomial multiplication in the vector multiplication or in the vector matrix multiplication. And apart from Kyber, there was one of the candidate algorithm that was Sabre. It was a third round NIST candidate. And there is another candidate that also used similar type of polynomial multiplication. That is MACT, that is one of the South Korean standard. So these two are standard algorithms which follows very similar mathematical hard problem, which is learning with error-based, like a variant of learning with error or learning with rounding-based problem. Apart from that, there is HQC, which is a code-based standard that also uses multiplication techniques. It's a similar polynomial multiplication technique. Although it doesn't have polynomials, but it does vector multiplication, but it also uses something similar, very similar. And complexity-wise, it's also very similar. Now, what comes into mind if I talk about multiplication or polynomial multiplication? What would you use? What is the most common one can be used? We have learned in schools. Can anybody tell me? Probably who are starting, that would be nice. Okay, if not, it's school book. It is school book multiplication. We just do multiplication, like in a very primitive way. Now, what would be the complexity of this multiplication? Can anybody tell me? Yeah. Yeah, it's n square. And how we can improve that, although I gave away a little bit in the previous slide, how we can improve that. But here, you see that the complexity is order of n square, and we do need the total, when we multiply A, let's say here it's four coefficient elements, and there is B, which is again a four coefficient element. When we do multiplication, then we create C that would have 7 coefficient, 7 coefficients. And then we would require this much memory to store all the coefficients. And when we go back to that domain, the ring, we have to do something called reduction. As in most of the PQC schemes, this ring is used, which is like ZQ that I told earlier. And that is reduced with this irreducible polynomial, which is x to the power n plus 1, where n is the polynomial size. Now, we have to do this reduction after we generate this resultant polynomial, because we want to stay in that domain. We want to stay in that ring. OK, this is about schoolbook multiplication. It can be used in many schemes when our n is very small. So when our n is small, then it's very efficient, actually. Now, a very, I'd say, very good algorithm over schoolbook multiplication is Karatsuba-based multiplication, where we actually could reduce from 4 multiplication to 3 multiplications. And that can be done by using these simple tricks. And if we use this multiplication, as we have reduced the multiplication, one of the multiplications from this whole multiplication, that reduces the complexity. And it can be generalized for higher, when we have higher, higher dimension, or I should say high amount of coefficients. Let's say here I was considering just two coefficients for each of the polynomials. When I increase this number, I take it n instead of this 2, then also it scales. However, the thing is, it scales, it becomes better for sure. And how we do that multiplication, that follows most trivial techniques that is used in most of the algorithm to optimize them. This is the divide and conquer type of strategy, right? And I'm sure whoever are from computer science department, they have used this type of optimization strategy in for many algorithms and many optimization techniques, right? So you'd be probably familiar with this thing. Now, we follow this strategy, and we keep doing that. Like here, I'm considering n is power of 2. It's I agree, it's a tricky thing we are considering already. N may not be power of 2, but then it becomes very costlier. So most of the PQC schemes, they use n power of 2, so that it becomes better to use divide and conquer or such type of strategies. And here, by using this, we actually, by using master theorem, we do need that theorem to reduce the complexity. It's easier if we have this, this reference. Here, let's say n is my input size, and I'm dividing a sub-problems, and I have n by 2 such sub-problems, and fn is some cost outside this operation, then my time complexity is something like this, and depending on fn, my complexity becomes something like this. So this algorithm I will use in Karatsuba, and after using this algorithm, as I showed in the previous picture, here, the complexity of this algorithm becomes order of in log 2 base 3. So whenever even if I increase the n, then also the complexity would be something similar. It's not, of course, it's not ideal. We would like to have, which is order of constant time or order of n, but we cannot have it with Karatsuba, but it's better than order of n squared for sure, right? So this is the best we can get with Karatsuba. But we can improve it. We can generalize it a bit more. How do we do that? This is the technique we mostly used. And this is called, what we can do, we can bring a polynomial from polynomial representation to point value representation, right? And if we take, let's say, we have two polynomials, A, which looks like this, and B, both are 2 degree polynomials. If we try to multiply them, we get this, and try to get C out of it, then C would have something like 6 degree 4, so 5 coefficients, right? And to get identify a 5 coefficient polynomial uniquely, how many points we would need? Right. So, and we can get that very easily, right? We just have to multiply these two numbers and get the resultant, like A and B, and we can get the resultant one. And the complexity of that is order of n. So it's very easy. We get an order of n algorithm. We get a polynomial multiplication, or let's say point-wise multiplication, just using point representation, right? Point value representation. However, although it is order of n, we do need something which will convert the coefficient representation to point value representation, right? I need some kind of mapping or some kind of function that would do that. And that is something which varies, and actually, like, let's say for like that is something which is little different for Tumcook, or let's say the number theoretic transformation that was discussed many times before in previous presentations. But this is something which is just different in these cases. So now I want some mapping which will convert this coefficient to point value, and I need that for Tumcook-based polynomial multiplication. And what they are called, that this coefficient to point value representation, how we convert it, we use evaluation technique, and for the inverse mapping, we call it interpolation. But it exactly does the same thing as we did manually in the beginning. Now, again, for evaluation, it's pretty much similar how we actually did it for the small example. But here, we would have a divide of some subpolynomials, which will also have some coefficient in it. So we divide a big polynomial into small chunks, and then we apply evaluation technique. Like evaluation is applied on that. So I choose, let's say I want to do Tumcook K-way polynomial multiplication. I would need to choose 2k minus 1 points. It's similar to how we did for 2-degree polynomials. We had to choose 5 coefficients, right? 5 points, right? It's very similar. And by doing that, we actually compute the point representation of those polynomials. And how do we do that? It's something like we use this type of mapping. Let's say I have chosen y1 to y2k minus 1 unique points. Then I need to do this polynomial, this matrix vector multiplication to get these representations. This is my output. And after that, I will multiply them. I can use any type of multiplication on them. School book or multi-levels of school book or Karatsuba, any type of multiplication. But here we will consider, let's say, school book multiplication we are performing. Or we can also keep repeating Tumcook 4-way multiplication until we cannot anymore. And the last step is interpolation. It's very much similar. It's like inverse mapping. So it's something like we do this inverse, multiply with this inverse matrix. And by doing that, we actually reduce the complexity. Let's say I'm using Tumcook 4-way multiplication, then it will make my complexity something like order of n to the power log 4 2k, but I mean 7, sorry, I'm bad at it. 7, like log 7 by log 4. Correct me if I'm wrong. Okay. I do not have it written here, but it is there somewhere, I promise. So anyway, this is like I just gave you an example, and somebody sees some similarity in between Tumcook algorithm and Karatsuba. A hint is the complexity. What do you think? Anybody? Right. Like if we put k equals 2, then this Tumcook 2-way multiplication is actually Karatsuba. It's the very same algorithm. It's like, as I mentioned in the 2-3 slides ago, that it is a generalization of Karatsuba. Okay, now we generalize to entity. How do we do that? In entity, we get a very good mapping. Like finding this mapping was hard, but if we get it, that makes our life easier. There we replace our evaluation with entity, number theoretic transformation, and our interpolation with inverse number theoretic transformation. And by doing that, we can actually reduce the complexity from something which is order of n to the power something, which is greater than 1, to a quasi-linear complexity, which is order of n log n. And to do that, we would require something called nth root of unity. That needs to be there in that ZQ field that I mentioned. And when we can get it, can somebody from math, I have seen someone from math, can he say that to me? Like when we can have that primitive root in the field? When can I have nth primitive root in ZQ? Yes, I need to be, like as n is power of 2, I need q as prime. Yeah, and that not always happens. So to use entity, we would require that. And that is the constraint. Anyway, let's say if we have that, if we have some parameters, which is, for example, Kyber parameter that satisfies because their Q was prime 3329 and N was 256. So for that, it satisfies. So for that, we can actually do this number theoretic transformation. For that, we have to multiply this matrix, which is generated by using this primitive root element. And we do this multiplication with our polynomial coefficients. And we finally get these elements. And we again do something called the divide and conquer type of technique. And we collect all the odd elements together and even elements together. It is represented even ones AE and odd ones AO. And by doing that, we are trying to create two sets, right? And most important thing that allows us to make it quasi-linear, that is this relation. As this is a cyclic ring, and then our W was a primitive root, nth primitive root in ZQ, then this relation will satisfy. And that leads us this equation. That makes our conquering easy and cheap. Okay, and that actually, as I mentioned, that makes our complexity much more less, which is order of n log n, which is quasi-linear. However, there is one small issue that I skipped. That is, sorry, I forgot to mention inverse entity, but it's very similar. For inverse entity, I just multiply the matrix inverse with the output of the multiplication, pointwise multiplication, and we have some such inverse. We have to scale down that factor, and finally we get our results. It's also order of n log n. So our entity and inverse entity order of n log n. So our total computation cost by total polynomial multiplication cost by using entity would be around order of n log n, because this is the largest one, right? Okay. Now I'll come back to the issue. So here, notice this ring. It uses ZQ by x to the power n minus 1, which is different in post-quantum schemes. Most of them uses something like this, which is x to the power n plus 1. So for them, we cannot use that cyclic property, right? Because in this case, our omega to the power n wouldn't be 1. We would require omega to the power 2n, 1, because we need omega to the power n minus 1, so as a primitive root. And then we would require something called negacyclic entity, and that is mostly used in PQC. For example, Kyber or dilithium or such schemes. And also many FHE algorithms actually as well. Now, what is different in this specific entity? There we need another mapping. We need this mapping as well. Let's say psi is our 2nth root of unity, then we try to get this mapping, and here psi square should be like it's omega, which is pretty much similar as our previous omega, like cyclic omega. And yeah, we have to use this multiplication. This is the mapping for negacyclic entity. Good thing is our inverse entity is also very similar, it's just the inverse. And the best thing is it also remains order of n log n. So Kyber can use order of n log n algorithm because it's also order of n log n. It does have a little bit more complex part. That is something like we do need more operation, we do have more constraint, we do need 2nth root of unity. But sadly, Kyber doesn't, like Kyber prime doesn't really have 2nth root of unity in that field because n is 256 and their prime is too small to have 2nth root. So Kyber uses something little different. However, this is my complexity that I just described, and I promised you that I'll give you this complexity, Tumcook 4 complexity. So these are main complexity, Karatsuba, Tumcook 1, and negacyclic entity. These are the main algorithms that are used in many, many post-quantum schemes. And it can be, like, if you implement it in software or hardware, this complexity actually matters. Especially, as I mentioned, when our n is too small, let's say 16, then school book is really better because we don't have much additional cost. But when we increase this n towards, let's say, a very big number, if it is like, let's say, 1024 or bigger than that, then we do need something like entity, which is quasi-linear, that would reduce our cost. But for 256, which is in between, for that Karatsuba or a combination of Karatsuba and Tumkuk-4, that also works pretty well. It competes with number theoretic transformation. Now, this is the polynomial multiplication that is used, those parameters I showed in the beginning. Now, my Kyber, as I mentioned, Kyber didn't have 2nth root of unity. So what it uses an incomplete entity, incomplete negacyclic entity. So the last layer, for which it cannot use entity, that uses something like Karatsuba-based multiplication. So it has it cannot finish one layer. It's a little, I would say, like a little compromise it has to make. And Saber is one of the schemes that I mentioned that uses Tumkuk 4-way multiplication along with Karatsuba and schoolbook, because small schoolbook multiplication, those are faster. And HQC actually uses, that is the code-based scheme, that uses Karatsuba mostly for smaller security levels, that uses Karatsuba, and for higher one, it uses Tumkuk 3-way polynomial multiplication. And another Korean standard that I mentioned earlier, that uses a very similar polynomial multiplication like Saber. So it's a Tumkuk 4-way Karatsuba and schoolbook. Now, apart from that, as I mentioned, like this is a very common algorithm that is used, like common polynomial multiplication trick that is used often in post-quantum schemes. Many digital signature schemes that also uses similar polynomial multiplication, although their field and polynomial size are different. Let's say for MLDSA or dilithium, that also uses a similar negacyclic entity, but that one is complete. And Falcon, it actually uses many polynomial multiplication. It has to. It uses, along with the entity, it also uses fast Fourier transformation-based polynomial multiplication. Does anybody know what that is? What is it? Yes. So actually, like entity is kind of like fast Fourier transformation. It is used in signals. It is very much used in many other applications. Entity is something like it's finite field version. It's very much the same thing, but fast Fourier transformation has its primitive root in complex field. So it's little more like, I'd say, little different. And if you need a combination of both algorithms, that makes it a little bit more expensive because you need those hardwares as well, right? And FNDSA is not the fastest algorithm. So yeah, but it also takes benefit from number theoretic transformation, and FNDSA, and FFT, both are like almost order of N log n. So the cost is pretty much okay, but it needs many multiplication that makes it costlier. Now, as you do understand from this up to this discussion, all those parameters that I mentioned earlier, those matters in terms of cost of the scheme, right? So what we decided to design a scheme by using those knowledge. And these are some schemes, some learning with rounding-based schemes, which is a variant of learning with errors problem, which is used in MLKM or MLDSA. We actually created 3 schemes, and there we use very different type of polynomial size and modulus and vector size. And by using this, we actually got some improvement in performance. So yeah, this is a little advanced thing I wanted to show you. Like by tweaking those parameters, you can actually get better scheme. And actually, it performs better in some cases, and also it also takes less amount of memory. So those design choices matters. And apart from that, actually, by tweaking these things, these parameters, along with the security and failure probability that I am cleverly avoiding, just to make this talk as simple as possible, by maintaining those, we can design another, I would say, a scheme that is better suited for lightweight applications where we do not need much security. So if you notice, and if you are aware of PQC schemes, this parameter actually provide less amount of security or least level of security. That is 120. It's equivalent to AES 128. So what we notice that if we tweak these parameters, then we actually get better hardware results as well. So our newly designed scheme Rudraksh that actually provided a quite good benefit. It was area efficient on hardware, and also it also provides time area improvement, and on chip also it provides very good energy area product, almost 5x improvement. So by tweaking those things, you actually can make better schemes. Now, up to this, I have talked about all the schemes. Does anybody have any questions about anything? Yes, you can do that. But I didn't mention one thing, that is reduction. As probably most of you know, if we have modulus, which is power of 2, for them reduction is almost free. But if we have an algorithm, algorithm for which our modulus is prime number, then the reduction is very expensive, right? Tim Cook uses a lot of reductions. So it can be useful. You can use that algorithm for when you, in Kyber, let's say, but the cost would be very high. It wouldn't be comparable to Saber or such algorithms which uses power of 2 polynomials, and power of 2 modulus. And as they use power of 2 modulus, they could actually almost get similar amount of performance result, which is very comparable to entity. But if you do not use power of 2, then I don't think that Tumku could give you that much benefit. So, and conversely, actually you can also use entity for power of 2 modulus, by increasing your prime number and keeping everything in between that big prime. But that does reduce complexity up to some point, but it increases area, huge area, it incurs huge area. So it's a good choice, but not the best one, I would say. So, yeah. Yeah, and also, another thing is reduction algorithm is something that, I have a colleague who actually spent almost half of his PhD on those things. We have so many reduction algorithms, and to make it constant time, okay, I'll be coming to constant time, but it's something it was mentioned in previous lectures, constant time implementation is very important, and making a constant time reduction, we cannot use just percentile Q, let's say, in implementation. We do need something called Montgomery or Barrett that makes reduction really costly for prime modulus. But for power of 2, it can just shift. Okay, now I'll go to side channel attacks part. And that is also on polynomial multiplication, but yeah, I'll try to just show how it is used, something like that, but very shortly, not too much details. Now, as I mentioned, constant time implementation, that is used to prevent timing attacks, as it was mentioned before. However, there are many more attacks, which Benedict touched in the morning. That is, attacks using power consumption information or electromagnetic radiation that leaks some information related to sensitive variables. Now, those algorithms are mathematically secure. These are implementation vulnerability, let's say. But implementation-wise, also we tried our best to implement during the reference implementation as well, right? We made it constant time. However, that making constant time is also expensive. However, making sure this power consumption, proving against power consumption attack, something like TPA or differential power attack or correlation power attack, those becomes harder and expensive. But if we do not do that, we have these attacks. Yeah, this is a paper that was published in ACM-TACS. They showed an attack, side channel attack, a very simple side channel attack, which is correlation power attack on most of the multiplication, polynomial multiplication that I described before. So without proper countermeasures, it's not secure. So we do need a countermeasure. And for that, I have masking. And I will introduce masking a little bit, and then I'll describe the cost of it and how secure it is after that even. So here, this is masking. Okay, don't be frightened with the slide. It's a simple one. Let's say this is a cryptographic algorithm. And how we do side channel attacks. Here we have a secret S, and let's say we are probing, trying to get information about what is going on. And we can probe once. Then we get some information about the secret key S by accumulating many, many traces. So by doing that, we get the secret key. However, it's also very mathematical, I'd say, probable secure model. So it's also very mathematical in that way. That is, we split this secret into multiple shares. Let's say we have S, and we split it into S1 and S2, where S1 and S2 doesn't have, those are independent. Only relation they have, that is S1 composition, S2 is the S. And if we follow the previous model and try to probe one of them, we get information about either S1 or S2. But we do not get both. Unless we get both of them, we cannot recompute the S, because S1 and S2 are independent. And to do an attack, we do need both of them. Although we can still attack it, but we cannot do the first attack that was described here. To attack this version, we would require 2 probes, where we can get S1 and S2 both, and then we can actually get the whole S. So a generic approach is used. Most hardware implementation cases, they use first-order masking, highest second order. But in software, we have to go really higher order as possible, because it depends on the noise of the device, how secure it would be. Now, in T-order masking, we split our secret into T+1 shares. For when we were using this masking, we split S into 2 shares. We tried to prevent first-order attack. For T-order masking, we split it T+1 shares, and an adversary here can probe up to T intermediate values. So even the adversary probe up to T, then also he or she shouldn't get any information about the sensitive variable. And we have to maintain that throughout all the operations that are used in cryptographic scheme. Our cryptographic scheme is not as simple as this one, right? So yeah, that's expensive. And another thing that is important in masking perspective, that is the operation. And what would be our composition, this composition, what is that relation? Depending on that, we have multiple masking techniques. One is called arithmetic masking, that is often used in arithmetic operations, where we split the sensitive variables into T+1 arithmetic shares. That means if we sum up in modulo Q field, then we will get our sensitive variable S. Now, as I mentioned, it is useful for modular operation, which includes addition, subtraction, and multiplication, which are mainly used in polynomial multiplication and also polynomial addition and many other operations those are used in, let's say, key encapsulation mechanism or digital signatures. However, we also have some bitwise operation, such as I mentioned in the beginning, that polynomial multiplication is our second most expensive operation. But what is our first or another most expensive operation is hash functions. And in PQC, as hash or extended output function, KECHAK is used, which is a bitwise kind of bitwise, that uses bitwise operations. So for them, we do need some bitwise masking techniques. And for that, we use Boolean masking. There, the relation is, if we do XOR on top of all the shares, we get back our original share. And it is useful for all those bitwise operations, such as XOR, AND, or shift as well. Because shift is a non-linear operation if we use addition, right? So yeah, that's why we also need Boolean masking for that. Now, this is our Kyber decapsulation operation. It is the same algorithm, the picture of the algorithm that I mentioned in the very first or third or fourth slide. It is the part of key encapsulation mechanism. It is the decapsulation part that the receiver uses after it gets the ciphertext. It uses a very long-term secret S, and if an adversary can recover this S by using the attack I mentioned on polynomial multiplication earlier, then it gets the long-term secret key. So once it gets it, it can generate any shared secret key. It can decrypt any ciphertext. So it would get the shared secret key that is the output of key encapsulation mechanism. So we have to make sure we keep it secure by using masking. And how do we do that? As I mentioned, we use both type of masking techniques, arithmetic and Boolean masking. But I will describe a little bit about arithmetic masking, how it is done very briefly. This is, let's say, I have two operand. I am trying to do an addition, and X and Y is my operand. X is sensitive, and is used, this operation is used here. So it's output of this and input of this. In that case, X is sensitive and Y is not sensitive. So, okay, sorry, forgot to mention. All the gray boxes, those has sensitive variables in it. And wherever there are no gray things, the output of it are not sensitive. So anyway, so we have two operand, X and Y. X needs masking, Y doesn't need masking because Y is secure, Y is public. And then how do we mask them? We just do share-wise operation. We add Y with X0 and all others can remain the same. We may need some refresh operation, but yeah, that is there. However, it's very simple, right? And that remains simple even if we have to mask Y, because we can just do something like this, Xi plus Yi for all of them. It also remains simple for multiplication when we have to mask one of the operand only. However, it becomes tricky when we have to mask both of them. Let's say we have something like X and Y, both need masking, both are sensitive. Then it becomes expensive because we have to do multiplication, like all this share-wise multiplication. That is, again, order of t square, t plus 1 square here. So that's expensive. But luckily, we do not need it because here in this algorithm, in all the multiplication, it's only one of them are sensitive. So it's good. But we do have a lot of nonlinear operations. I wouldn't talk about them, but they exist here. I'll just quickly show where we are using arithmetic masking and where we are using Boolean masking. Here, I use color blue for arithmetic masking and color orange for Boolean masking. As you can see, all the arithmetic operations are using arithmetic masking. And these XOF or G, those are KECHAK based. They are using Boolean masking, along with some other operation like centered binomial distribution and many other sub-operations. And we have some shift here and here that that is compression operation. So yeah, those are very expensive. We do need some conversion algorithms. Like this is some component that is introduced due to masking, but one of the expensive operation in masked implementations. So it's something that just came out of nowhere, but become a very important and expensive block in secure implementation. Now, this is the performance results for Kyber, and as you can see, the orange line represents Kyber. It is the unmasked one, so where there is no countermeasure. Then I have first order, second order, and third order. If you see, it increases gradually, and it increases quite a lot. In this figure, it's not that much visible, but you can understand, right? From unmasked to masked, for first order even, it is becoming really high. And that increases quite a lot for higher orders. However, yeah. Sorry? It's T. Like instead of T, I'm putting like 1, 2, and 3. How many shares I'm using? Yeah. It's normally like shares are used to prevent the attacks. So we use like T plus 1 shares to prevent against T order attack. So this first order has 2 shares, second order has 3 shares, and similarly it increases. Now, for a reference, we actually also implemented, like in one of our work, we implemented the other scheme, Saber, and that uses a power of 2 modulus, and we show that it actually increases less compared to a prime modulus-based scheme. So if we need a secure implementation, in that case, power of 2 based schemes is actually better. That's what we show in one of our work. But yeah, this is something which is, I think, important when we have to go for secure implementation, which is very much needed for embedded devices. But we actually found out of another attack point in this secure implementation. That was, this secure implementation actually provides security against side channel attacks. But there are many different physical attacks. Another one is fault injection attacks. And we observed that one of the masking component that was introduced due to masking, that introduced a fault attack vulnerability in this secure implementation. But that doesn't exist in insecure one. So masking is not a foolproof countermeasure in that way. And we do need to consider all different type of physical attacks to provide protection against them. So it was the conclusion of this work. Now I'll quickly go to the conclusion and summarize it. That is, first, in this talk, I showed a generic design of key encapsulation mechanism that is used in most of the key encapsulation mechanism, which are NIST standard or other standards. And here, as I mentioned, polynomial multiplication is very important and expensive component for most of the post-quantum schemes, at least the ones I mentioned here. And apart from that, also, there are many schemes for which multiplication is very expensive. For example, Frodo, or let's say any other digital signatures as well. Probably not for the MPC in the head-based one, or let's say sphenes or those hash-based ones. But apart from them, for most of them, multiplication is the most expensive operation. And protection against side channel attack, that is important for sure. You already got to know in hardware session. But we also need to know protection is very expensive. That's why we cannot use general protection. We have to optimize it as much as possible, and also need to consider other attacks which are possible in that physical environment that is there. And try to analyze different advanced attacks which are there, but it's very primitive attacks right now. And unfortunately, there is no countermeasure, or the countermeasure that exists, those are also not very much verified. and still in the process of development. So we do need many, modified or improve. First, we need countermeasures, then we need to improve them. But we currently, as far as I am aware of, there is no fault attack and side channel attack secure countermeasure for PQC schemes. And even for many schemes, even side channel attack secure countermeasure doesn't exist. There are many schemes which are still vulnerable to timing attack as well, even though they are verified thoroughly during the competition, but still there are those vulnerabilities. So I really stress the importance of examining those schemes. Okay, that's all. Thank you.